Hello, my name is John Koeter. I'm the Senior Vice President of Strategy and Marketing for the Solutions Group at Synopsys, and welcome. It's a pleasure to virtually talk to all of you. I miss so much coming to Israel and to Europe. I visited there many times a year, typically before the whole pandemic hit, and I look forward to doing it again. Today, I'm going to be talking about how IP is powering the next generation of chip designs from cloud to the car. So first of all, let me talk about some of the major changes that we are seeing right now in the data center. There is a gigantic shift that happened by the pandemic. So today, at least according to Gartner DataQuest, about 90% of the applications are being run on on-prem clouds. And over the next 4 to 5 years, we expect that to really flip and have almost 80% of the applications being run on the public cloud. And that is just driving a gigantic shift across the entire semiconductor industry. And it's creating amazing opportunities for all of us who work in the semiconductor industry. And I'm going to talk about just a few of those in the next couple of slides. But before I do that, I'm going to talk about how the data center is really driving new design starts and innovation. We're really, I think, in kind of an almost golden age of semiconductors right now. The innovation levels are just so high, driven by that dynamic that we just talked about, whether it's AI accelerators or graphics chips or next generation server chips or smart NICs, you name it. There's so much innovation happening right now, and it's creating a great opportunity for all of us. As we can see from this IBS Global Semiconductor report right now, if you look, we're right here in the area of 2020-21, about $80 billion worth of opportunity for semiconductor, and that's expected to roughly double over the next 5 or 6 years with a compounded annual growth rate of more than 10%. And we're also seeing that there's a rapid evolution of processes to go along with that. Today, many of these design center chips are in 7 nanometer, but we're also very, very rapidly seeing them move to 5 nanometer and 3 nanometer. In fact, numerous foundries really are saying that high performance compute or cloud compute is really going to be the driver for their next generation of processes. Now, one of the things that I also wanted to talk about is the explosive growth in artificial intelligence. We all know that artificial intelligence is here, and it's really revolutionizing every aspect of the semiconductor design process. And one of the root causes that is happening, being driven by AI chips, is that you're going to need to move an incredible amount of memory on and off the chip, and you need different types of memory compute. And this is driving a tremendous shift in the way our customers architect the design. It's also driving a tremendous shift in the way people think about storage. You can see on the graph here just a massive growth in compute and memory needs that are driven by these very, very complex AI algorithms. Now, one of the things that is growing, as I mentioned, because of this is enterprise level storage, which is growing at an almost 18% CAGR, 17.8% to be exact, from 2019 through 2024. And SSDs are rapidly transitioning into different new semiconductor processes as well to keep up with this tremendous demand. So today, many enterprise SSDs are in like a 16 or 12 nanometer node, but that's rapidly shifting to 7, 5. And we see an adoption of 3 nanometer as well in terms of the data center being driven very, very aggressively by these enterprise storage applications. Persistent memory is a new, really important trend here, and that's being widely adopted for low latency storage and large memory applications to augment DDR. SSDs being driven by the need to handle all of this data are moving from PCI to PCIe 5.0, and in some cases even PCIe 6.0 to handle the system interface and to handle all the data coming on and off the chip here. And compute storage is fundamentally changing, and arrays are going to be handling more and more of the compute data storage as we move forward. So just a tremendous amount of change happening in every aspect of the data center, being driven by, among many other things, artificial intelligence and the increased usages that we talked about over the last couple of slides. Now, specifically, I wanted to double click into one more area of memory, which is this is more on-chip memory interfaces, externally driving external DRAMs. So there's many different options that our designers have. You can have DDR5, which has by far the biggest capacity. You can have LPDDR5, or rapidly evolving now into LPDDR5X. That has excellent low power characteristics and is popular in applications such as high-end mobile as well as in automotive. You have GDDR6, which is certainly a contender in terms of a trade-off between bandwidth and latency, and the fact that it doesn't require any kind of interposer design. And if you're just looking at flat out raw, highest performance, highest bandwidth, and things like an AI training engine, that's where HBM3 just really shines. No other memory technology delivers the same kind of total bandwidth as HBM3 does. Now, of course, it does require complex packaging, and that's actually another major trend that's happening in the semiconductor industry right now, as many people in the supply chain are looking to reduce the cost of these 2.5D or 3D packages. And we're just seeing just an absolute explosion of innovation in the packaging area. Now at Synopsys, we're really focused on DDR5 because of the capacity in things like a server chip, LPDDR5, 5X for the mobile and application and automotive applications, and HBM3 just for the raw bandwidth. Now, I wanted to also talk about a brand new trend in semiconductor that's going on, which is the system in package, or SIP. And really, it's the new SoC. So today, chips are getting very large and very complex, and they're hitting the reticle limits in some cases. And these chips are being split into multiple chips. We call that a homogeneous use case. So think about something like a big Ethernet switch chip or something like that, which is being split into multiple chips. And in that case, really what you want the die-to-die interconnect to be is essentially like an extension of your internal bus. You want it to be very fast, very low latency, very error-free. So that's driving one class of die-to-die connectivity solutions that we offer here at Synopsys. But there are other use cases, what we call disaggregation use cases, where what used to be a monolithic, let's say, server chip that had the CPUs on it and all the I/O chips is now being disaggregated into multiple chips. So you might have the main server chip that's continuing to race to 5 nanometer to 3 nanometer, and then you may see the I/O chips that surround it being put on a separate chip, and maybe let's say 12 nanometer or a 7 nanometer technology. So this system in package, or SIP, is really driving significant changes to the way the basic architectures are being designed. And one key to making SIP work is to really have very high speed, very low power, very low latency, error-free die-to-die interfaces. And that's one of the things that we're investing in very heavily here at Synopsys, whether it's a parallel interface or a serial die-to-die interface. Now, I just wanted to come back and summarize all of the IP that we have for high performance compute that is being driven by all these trends in the market that I just talked about. So we have very high speed SerDes up to 112 gig and long reach capabilities here. And that's for things like top of rack applications. We have for memory interfaces, we have DDR5 being used in things like server, where it's all about capacity, or LPDDR5 or 5X, where it's all about low power, or HBM3, where it's all about bandwidth. We also have global memory structures here that we optimize specifically for high performance compute. We have TCANs, we have multi-port memories, again, which are very important in things like networking applications. I talked about how we have both serial and parallel die-to-die interfaces as well. And then, of course, we have the system interface, the PCIe 5 going to PCIe 6, along with CXL, which is used for many other things, including cache coherency. And we're really seeing a lot of increase in demand for CXL. And one thing that was brand new that we just introduced was security modules for PCI Express and CXL to really secure that system interface into the chip. So we have a very, very robust performance portfolio of IP here for high performance compute. Now I'm going to switch over to the car, where just as significant a number of trends are happening right now. It used to be in years past that there might have been 30 to even 100 ECUs in a car. And then those ECUs started to consolidate, and they started to consolidate into controllers like the comfort domain controller, the powertrain controller, the ADAS controller, the infotainment controller, or the connectivity controller. And that's kind of today's state of the art, design, where you have these big chips that are being switched through a gateway. And they really consolidated all of those individual ECUs that we talked about in yesterday's car. But where we really see the automotive industry moving is into these new, what are called zonal architectures. So you have a zonal gateway, and then you funnel all of the data coming into a central processing module. And that's really fundamentally changing how we go about architecting the chips and the demand for those chips in terms of processes. Today it's very common for high-end automotive chips to be in like a 16 or 12 nanometer type of process. That's rapidly moving to 7, 5, and even 3, driven by these centralized processing modules, which are further consolidating the ECUs. Now, when it comes to automotive, we all know we're on the path to self-driving cars. It's going to be a long path. It's not going to happen tomorrow. But one of the things that's really important here when we did a survey of what is one of the most important factors when you're developing automotive chips. And, no surprise, topping the list here at almost 80% was meeting all the safety requirements and processes for automotive applications. This is not a trivial task. This is something semiconductor partners have invested in for very many years. But along with that, the compute requirements are going up so high that optimizing the power for a given performance is also becoming just equally important. And so at Synopsys, we're looking at these challenges and we're designing solutions to these challenges. So one of the things that I wanted to do is just take a quick case study in terms of an ADAS. So ADAS is one of the most popular and growing applications within the overall automotive. As I said, no surprise, in the ADAS chip, safety is mission critical because it is all about helping the driver to be more safe. But also power is really important within an ADAS chip, simply due to the fact there is so much functionality going into an ADAS chip. The vision processors, the amount of on-chip memory, and so forth is just exploding. And so therefore, you really have to look at your power envelope. And so when we have invested very heavily at Synopsys in automotive IP, we have a very rich portfolio of IP that's been certified for ASIL B or ASIL C or ASIL D, depending on the particular type of IP. It's also ISO certified. Our entire development processes have been certified by an independent external auditors. So this is something where we have taken it very seriously and have invested very significantly in creating a very wide range of what we call automotive grade IP, from the processors, and I'll talk about an example of that next, to memories and logic libraries, to interface IP such as Ethernet and LPDDR and PCI Express and HDMI and USB, and so forth, to integrated safety and security IP, which is what I'm going to be talking about here on the next slide. So one of the things that we have created to help our automotive customers is we've created a functional safety solution that is ISO 26262 compliant for automotive. And so at the heart of it is a safety island based on our ARC processors. We have multiple cores running in lockstep looking for errors. And this is just not at boot time, of course, this is at real time. It's constantly monitoring every 5 to 10 milliseconds as the car is in operation, looking for any kind of faults. Then we have a dedicated test network that is being driven by our embedded test applications such as SMS, Star Memory System, and SHS. And so what we do is we work with our customers to put these safety wrappers around the IP that's already automotive grade certified. And then we create code that then runs onto the safety manager. And the whole system here is continuously looking for faults and taking corrective action if it does find fault. So this is a fully integrated solution from Synopsys that's really going right at the heart of some of the things needed by ADAS in terms of ensuring the safety of the vehicle. Now, I wanted to also just conclude this presentation by saying we've had a lot of success in automotive, and we've been lucky and fortunate to partner with some of the leaders in this industry, including Infineon in their next generation Oryx 3G platforms, including Qualcomm in their relatively recently announced Snapdragon Ride platform, and here in Israel in Arbe Robotics, who is a leader in high resolution imaging radar. And we work very much closely with them to have the highest levels of safety for their chip. So we're having great success in automotive. We have a very broad portfolio. We're working with many excellent customers. And we're continuing to be committed to drive this forward as cars continue to evolve. So with that, I just wanted to say Synopsys is really your trusted IP partner. We have complete solutions. We have the broadest portfolio of IP on the market. We're dedicated to the highest quality of IP. We have a small army. Some people might joke a large army at 4,500 plus engineers working on IP. And we're really going after and doing what it takes to be successful in all these new areas we talked about, whether it's automotive or cloud or server, high performance compute, IoT, 5G, and so forth. So with that, I want to thank you very much for your time and your attention.